Welcome to this ELV Engineering Explainer. Today, we're diving into Power over Ethernet, or PoE, specifically for CCTV systems. You know, it's that brilliant piece of technology that lets us run a single cable for both data and power. Sounds great, right? But here's the catch. It's also the exact technology that fails the most often when it's poorly engineered. So in this explainer, we're going to completely bust this myth of generic PoE compatibility that literally causes catastrophic system failures out on site. Let's get into it.
Okay, picture this real-world scenario. You've got a perfectly specified pan-tilt-zoom, or PTZ camera. You commission it, everything works flawlessly. But then, why does it suddenly drop offline on a freezing cold morning? It's a notorious issue, and honestly, it catches out even seasoned engineers all the time. Spoiler alert, the answer isn't a faulty camera. It's almost always a fundamental failure in power engineering. To figure out exactly why this happens, we have to look closely at how power classes and standards actually dictate how your system behaves. So let's take a quick look back. In 2003, we got IEEE 802.3AF, or Type 1 PoE. It pushed up to 15.4 watts at the source, which, was plenty for your basic fixed cameras back then. But by 2009, as cameras started getting a lot more complex, we saw the rollout of 802.3AT, which you probably know as PoE+, or Type 2. That bumped us up to 30 watts at the source, giving us exactly what we needed to power those PTZ cameras with built-in IR heaters.
But of course, the tech didn't just stop there. Enter IEEE 802.3BT, better known as PoE++ or 4-pair PoE. Now, this standard completely shattered the old design methodologies. We suddenly had two really heavy-duty power levels. Type 3 delivers up to 60 watts at the source, perfect for a high-spec PTZ running all its features at once. And then you have Type 4 pushing a massive 100 watts at the source. That is the exact mathematical precision you need for really heavy devices like thin clients, displays, and those ultra-high-end multi-sensor cameras.
Now, all these standards translate into strict device classes, going from Class 0 all the way to Class 8. What's cool is that devices actually talk to the switch and declare their class during negotiation. So a basic camera is Class 1 at 4 watts. Your standard PoE fixed camera, Class 3 at 15 watts. A PoE Plus PTZ sits at Class 4, drawing 30 watts. And those heavy PoE++ devices occupy Classes 5 and 6 at 45 to 60 watts. Here's the absolute crucial point. Writing generic PoE compatible on your bill of quantities means absolutely nothing. The switch relies heavily on these exact class numbers to allocate power correctly. If you aren't specifying the exact class, you are basically designing a failure waiting to happen.
But hey, power isn't just about what's coming out of the switch. It's heavily tied to your physical infrastructure, namely the 90-meter rule. While Cat 6A cable is technically rated for 100 meters, PoE loses power as it travels. Push it past 90 meters and you get hit with a severe voltage drop penalty. And what happens when a camera under heavy load hits that voltage drop? It resets. Boom, gone. So you absolutely must design your cable runs to stay strictly within 90 meters or start planning for PoE extenders. And beyond just length, we've got the cable category penalty. Look, you cannot run a massive PoE++ load on an old Cat 5e cable and expect it to be stable. Cat 5e is hard capped at Type 2 maximum. Cat 6 is limited to Type 3 loads. For true PoE++ Type 4 stability, Cat 6a is mathematically required, period. Which actually brings us right back to our cold morning scenario. A PTZ camera with a built-in heater is going to pull its absolute peak power on a freezing morning. If your switch is sitting comfortably at a 90% budget utilization, that sudden heater spike triggers an immediate undervoltage across the whole switch. The result? Your camera reboots exactly when you need it the most.
All right, so let's dive into the switch power budget trap.
Here's a real wake-up call of a question for you. Can a 48-port switch specifically advertised with a 740-watt PoE budget actually deliver power to 48 CCTV ports? Manufacturers absolutely love marketing these switches, but if you do the math, a 740-watt budget physically cannot deliver 30 watts to every single port. Think about it. 48 ports times 30 watts is 1440 watts. If you actually try to pull that, the switch is going to aggressively throttle power across the board. Let's break this down further. Imagine you've got a site with 48 cameras to connect. Let's say 40 of them are fixed cameras, right? So that's Class 3 at 15 watts each. That puts us at 600 watts. Then you have your remaining 8 cameras as PTZs, Class 4 at 30 watts each. That's another 240 watts. When you sum up that simultaneous peak load, you hit 840 watts.
And guess what? That 840-watt load completely breaks the specifications of your 740-watt switch. It's mathematically impossible.
So your system is mathematically undersized. But hey, we're engineers, right? We fix things. The exact solution here is pretty straightforward. You either need to upgrade your core to a single 1,000-watt PoE++ switch, or you take that 48-camera load and safely split it across two 24-port switches, with each one having its own dedicated 740-watt budget. Now, how are we actually injecting that power? Well, N-span PoE is your standard approach. That's where power is injected natively straight from the switch port itself. On the flip side, mid-span PoE relies on a totally separate inline injector device. Let me give you a firm design directive right here. Avoid mid-span in new builds, for sure. You really should be reserving mid-span injectors strictly for retrofit projects, like when you're upgrading an old non-PoE switch and just need to power one or two cameras. Keep it clean for new builds.
All right, let's keep this rapid-fire math going because we absolutely cannot forget about uninterruptible power supplies, or UPS sizing. Remember, the switch itself draws power on top of your PoE loads. So if your camera load is 600 watts and the switch itself needs 740 watts to run, your total load is actually 1,340 watts. Now, if your client is demanding a 4-hour battery backup runtime, you multiply that out and get 5.4 kilowatt hours, meaning you must specify at least a 6 kVA UPS to actually survive an outage.
Here's another really practical field design directive, especially if you're working in highly demanding environments. Say you're designing for a 5-star hotel. You want to limit your intermediate distribution frames, or IDFs, to just one 48-port PoE++ switch per floor maximum. I mean, even if you could technically plug all of a floor's cameras into one massive rack, don't do it. The sheer amount of power, the resulting heat load that needs intense cooling, and just the physical patch panel space dictate that you really have to spread that load out across multiple IDFs. So, as we wrap up this explainer, let's just quickly recap the fundamental blueprint for building fail-proof networks. It boils down to 3 golden design rules. Number 1, always specify the exact PoE class per camera right there in your bill of quantities. Number 2, your switch power budget must equal the simultaneous peak sum of all your devices, never just an average load. And number 3, make Cat 6a your absolute minimum standard for any PoE++ deployment from here on out. And finally, I'm going to leave you with this somewhat provocative thought. Power is invisible until it fails. As ELV professionals, you literally have to engineer your power systems as if the entire network depends on it, because honestly, it absolutely does. Thanks so much for joining me in this explainer. Keep building your expertise and make sure your next design survives the wattage trap.